Hey, this is Mr. Robotic Warfare. Hi, JGGames. I am here to explain to you this little thing that I've created because you've expressed a little bit of an interest in it. Thank you, by the way. It does really mean a lot. I've been playing this game for a while, not nearly as long as you, and Combinators came out, and I think they're pretty cool. So, this is my little creation here. This is sort of the sum of some various concepts that I've figured out. A couple of side notes before we begin. Number one, technically this is a cop-out. The display driver that I have right here for this 7-segment display is really meant to work with BCD. And I was trying to get some BCD together, and I sort of got stuck. So I decided instead of doing that, just use 4 binary bits and translate it directly. So I got the second digit here configured, and I'll go through that. But technically this is a cop-out. I'll show the shift register at some point that I created, and that's probably what, if you were to contribute to this with me and maybe give me some advice, it would be on how to create that. But anyways, functionality wise, what this is it's a little adder. It adds 2 numbers, and right now, because of that thing that I did with the BCD, or the lack thereof, the maximum sum of the number can be 15, because I sort of slacked off. Anyways, so your 2 inputs are these 2 smart chests right here, 1 and 2, and you put gears in them. I just like that. So you can put a specific number of gears in them. So if you put 1 gear, it'll register as 1 gear. You put a second gear in, it'll register as 2 gears. And to sort of show that this is relatively well oiled, I'll just I'm using the test mode mod and your resource mod, just to sort of show off, to be able to build all this stuff without having to actually play the game, which means that the inserter stack size bonus is on, so I have to use a belt. So let's get 15 gears into this chest here, and as they enter one of the inputs, it's counting up. The reason that it does that little flicker thing is because of the way the adder works and all this stuff. This is nowhere near perfect. This is mainly just a proof of concept, but it counted up to 15 here. So next, the adding function, which is relatively simple to show. So let's just take 8 out of here, so we've got 7 left in there, and put the other 8 in the other chest, and we have 15 once again. The way that this works is it's just these two convert the number of items in the chest to a 4-digit binary number, and it goes through an adder and then to the 7-segment display driver. So just for a little more, let's go take 4 out, so now we have 11, 12, 13, 14. It's just an adder with that stuff. If you overflow it, which is unfortunately only greater than 15 right now, so we've got 15 here. If we overflow it, I did this little bank of lights here for overflow, and it'll still stay off. Alright, I'm gonna try and start explaining this thing. I'm sorry if I don't do this adequately. You've got far more practice narrating than I do, but please bear with me. So let's go ahead and turn that on. So the first thing that I want to talk about is this little thing right here, which is the number of the items in the chest that gets down to a 4-digit binary output. And this is how I originally prototyped the thing. I did not spread these out as far as a design because I actually don't have any blueprints left of that. I can look to see if I've maybe got one of the ones from my original prototype, which would probably be a lot better. This is there's something else. Adder's over here, but it's the same configuration. I'm sorry, I just wasted your time. Beep beep. Okay. So, back again we go. Faster. Okay. So this is the This is the thing that converts it from number to binary. So what happens is, I'll try and do the best I can. The way that this functions is, basically what it does is it looks for each bit. So each bit has a number associated with decimal. I'm sure you know that. So the fourth bit has 8, 4, 2, and then 1 at the end there. And the reason that this one doesn't require a full thing is because of the way that I do this. So essentially what I do is for each bit, I check if the number of items in the chest is greater than or equal to that number. And if it is, then I subtract that number and pass it on to the next. So essentially if you get, call it the number 10, no, that's not a good idea, 13, you get, so you pass 13 to this, it checks if it's greater than or equal to 8. It will, it'll take 8 out. You have 5 now. It's greater than or equal to 4, so it'll take a 4 out, pass a 1 through the 2. Since it's not greater, it'll just pass it straight to the 1. So the way that this works is you always end up with 1 coming from this output, and you just have this gear set up to 1. Because of this, this is a tileable design. It can work for many, many, many bits because you can just keep chaining them together and changing the values of what number it checks for. And the way that I can demonstrate this is I'll do the 13 example like I said. So here's your 13. And if we actually max this out to 15, you see that this turns on. It actually passes 1. And the output signals, it says 1 there. So it's passing 1. And if you actually look at it, you have 15 here. It's passing 7. And then it's passing to 3 because it takes another 4-way. Now it's passing 1. If you actually max this out to 16, it'll turn off because this actually passes a 2. So it's the same sort of thing, and it can work on down the line. As far as how exactly it works, the way that I decided to do this, because you only have access to the 3 different equalities, equal to, less than, or greater than, and I want to test greater or equal to. So the one way that I could do that is I could test if it's equal to, greater than, and then or the values. But I actually decided to do something different because that would take 3 combinators, and I found a way to do it in 2. So because we only have 3 cases, equal to, greater than, or less than, I want to check if it's 2 of the 3 or not 1 of the 3. So that's what I do here is I check if it's less than, and then I invert that with this. So we're taking the gear here. This is a constant combinator, and this is one of the places I use coal for part of the operations here. So this is how part of the reason that I control, and I believe there's another one here. This adder adds the same number. I suppose that I could make this a little more efficient by actually having it add the coal, which would mean that you could just change the combinator in each row. I need to make a note of that. Past that, I really hope I'm doing a good job narrating this. I'm really sorry if this is boring you, but it checks if it's less than or equal to, or less than. It inverts that. So if it's less than, output 1, 0 to 1, so that's inverting it. And then what it does is it adds it to the, it adds 8, so it adds the value of the bit to the original number. And then it passes it down here, and we actually take the same value coal here. So essentially what this is doing is it's saying greater than or equal to. Okay, so if it's not, you get a value of 0 passed through this, so you get 8. So we have this value 8 here, and 8 is not less than 8, it's equal to. So it doesn't pass on the coal value, and that doesn't happen. If it is greater than, it'll make the red signs packs 9, and 9 is greater than 8. So it'll pass the 8 coal signal along to this, which will subtract it from the original number of gears, and then pass it on. You'll get the world download, so I think I'm going to move on to the next part, which is the adder. This is the adder. This is fairly simple. It's just the way a full adder works. You've got these ones are XOR gates. The equal combinators are XOR gates. The greater than, these 2 greater thans are AND gates, and then this is the OR gate. So you've got your 2 inputs here. The top light here is drop, and the bottom light here is carry. So it works exactly as you would expect it to. 1 is 1, 0 plus 1 is 1, 1 plus 1 is 2, or carry it out, and you can in fact set up a carry here. Let's see if I can do that. I want this to be like so. Hopefully that'll make it work. Yep, there we go. So this is carry, and that comes from the next bit in the little bit of a bigger design I have here, which is right over here. So it does in fact come down for the next carry, and it puts it into the respective place. So the adder, pretty straightforward. I'm assuming that you know how the logic gates work as far as this game goes. So that's XOR. We're inputting gears. This is and then this is OR. And it's wired the exact same as a full adder. So that's that. Okay, so this is where we sort of get to the cop-out. Essentially, this is modular. All of this is modular. And this, just one of these, this one big strip is technically what's the module. I sort of added this. I call it cheating, but it's still an accomplishment. Right here, this is to make the 2-digit number work just within the constraints of this. Once I actually get some form of BCD working, then this is how it's going to work. But this is fairly simple. It uses a very cheeky trick that I figured out, which is that it'll take... this is outputting, actually. Yeah. So what this actually does is it takes a binary number and then turns it into decimal as far as the game is concerned. So if we have a value of 1 here, it'll pass a 1. If we have the second bit of value of 1, which is 2, it'll pass a 2 into the system. And the way that I manage this is, let's just use 2 for example. So I'm passing a 2, but this is a 1, so it gives a 1 value. So what basically I should not be using gears, is what I should not be doing. There we go. So pass in a red science. Add 1 to the red science to give it the actual number 2. So this one adds 0. I do this a lot. I have an empty for 1. So instead of doing this, I would actually have had a whole nother unit. This is an extraneous unit, but I did it for continuity's sake. So you add 0 here to get the value of 1, add 1 to get 2, add 3 to get 4, and add 7 to get 8. And I decided to use fish as the output. So the way that I've gotten around this, converting a bit into the number corresponding to that bit. So this is technically, this top half here is technically a binary to decimal converter. So what I do is I take the number and get it to that number, and then what I do is I multiply it by the original bit. So the fish become the actual number that's desired. So in this case, I've put a 2 in. So this is outputting a signal of 2, fish. So that's the number that I want. And then I multiply it by the original value, in which case it's either a 1 or a 0. So it either passes the output or it does not pass the output. I hope that makes sense. I probably did a very bad job of explaining that. But basically, the reason that this is necessary is because having these adders, you're going to have an output of 7 fish. You're always going to have an output. But by multiplying it by the bit originally, you multiply it by 0 when it's not there, so that 7 is basically irrelevant. Anyways, so we put a 2 in there, and you can see that it's made a 2 down on the display there. So the way this works is simply, these are technically the 4 outputs of the binary to decimal conversion. So you have a number here, so each bit gets transferred into a decimal number. And as I'm sure you know, when you tie more than one input to a combinator, I can just demonstrate this real fast. If this insults your intelligence about the game, I'm sorry. But say that we have 2 things connected to the same source, and if you, let's call this, we want it to be 5 equal to 5 let's not do red circuits, I don't have any, gears. So we want to have this equal to 5 gears. It doesn't matter how you put it, it sums the lines of the value. So even if I have 2 here, I can put 2 in a different place, or 3 in this case, and they'll actually add together in the wire. which is extremely useful. So basically you have the numerical bits outputting here, and they all add together. So if we go down to the display here, this is a traditional 7-segment display, and each one of these segments it's numbered clockwise and then in the middle. So this is 1, 2, 3, 4, 5, 6, and 7 in the middle. And I decided to actually use the signal numbers because it was convenient, because it made sense. And then the reason that this is cheaty is because I actually only used the first 3 here. So I use 8, 9, and 0, and I don't use the rest of it. So essentially what this is that each number, so in this example, we'll use 2 again. To create the number 2 on this 7-segment display, you need the first, second, 4th, 5th, and 7th to create that. So essentially what I have is I have this whole big cluster of combinators. Let's see if I can find the number 2. The number 2 should be right here. No, that's the wrong side. So here's the number 1. If the red science pack equals 1, you output 2, and the next one, so basically for each segment, for each number, there's a combinator. So in my example of 2, if you look of all the combinators that have 2 red science packs, there's 1, 2, 4, 5, and 7, just like I said. So if we put 2 in here, or we put a bit of 2 in here, all of those combinators are going to go high. So we have output signals here. So it outputs each of those, and then that goes to the corresponding thing, and that makes plenty of sense. It goes the same thing for all of them. So demonstration works for 6, because the actual row is right where? Here it is. These are some of the 6 ones. And then 7 makes plenty of sense. Okay, so once we get to 9, let's do that real fast. What happens is, well, first of all, I should mention this little slice in the middle here. These are a couple 1s and 9 because I counted wrong initially. This just checks if it's 0, and if it is, it'll turn on that middle segment, which is why when you have it all empty, both the displays have that little line down the middle. That's easily disableable. I just thought it was cool. So if we have 9 here, going over to the second display, these 3 are irregular and the rest is all the same. So this is just checking for 10. It'll turn on the corresponding lights, but here's the trick. First of all, if it's equal to 0, it's the little middle strip again. These 2 are connected together, so the number from here follows into the inputs for here. So it checks if it's 0 and turn on the little middle strip. Here's the little cheatsy thing that I did, which is that for every number greater than 9, there's only going to be a 1 here. So essentially what it is saying that if it's greater than 9, you just turn on 8 and 9, which are these 2 strips. So for all numbers greater than 9, it's just going to turn a 1 on. And the rest of these are to turn on. It's connected here, if you can see this green wire that's across my head right now. That just goes back to these outputs. So it's essentially the same exact thing. I just did this little doohickey because I didn't want to spend the time to make BCD quite yet. So it's just the same sort of thing. That is essentially it. Let me know if you have any questions. I'm hopefully going to be able to find a way to get a world download for you. I'm not exactly sure what form that'll take, but it'll be in the description of the video, hopefully. So, yeah, that's pretty much it. Thanks a ton for listening to me ramble and taking the time to deal with this. I really do appreciate it. So, I hope to talk to you soon, and thanks for watching.